Good morning. I'm eating a Nature Valley granola bar, and I gotta tell you, these things have the most crumbs of any granola bar I've ever eaten. It's like you just open the package and it just explodes with crumbs everywhere. Has anyone experienced this? Am I the only one? All right. I know we don't have the full class here yet, but I'm going to go ahead and get started anyways. This is AP Physics 1, 413, period 6. I'm so hungry though. More crumbs. So what we're going to do today, we are reviewing for the AP exam. And we're also talking about experimental physics. Today's review is going to focus on forces. So we're going to have a review of forces first. And there are two problems pertaining to forces that I think are the most important in order to sort of demonstrate mastery. The first one is the inclined plane. All right. So just to remind you what an inclined plane is, you have an incline of some kind. It makes an angle theta with the horizontal, and then we put a block on that incline, and it slides down. And what we want to do is we want to know what is the acceleration of the block. So obviously the block is going to slide down in this direction. So I'm going to call that the positive direction. All right. So notice how the positive direction is not horizontal. It's actually slanted. So the first thing we're going to do is we are going to draw a free body diagram. And what a free body diagram is a picture of the forces that are acting on an object. So this block is going to have three forces acting on it. One of them is the weight force, which goes straight down. And the size of the weight force, if you remember, is mg. The next force is the normal force. The normal force prevents the block from just falling straight through the incline. Okay, it's a force of contact between two surfaces. And it always goes perpendicular to the surface, so it's going to point perpendicular to the incline, like so. So that's F sub n. And then, so these two are going to be the same no matter what, but friction could change, okay? Because this block, we're assuming it's sliding down the incline, friction is an oppositional force, so it goes up the incline. All right. And furthermore, we learned about two different types of friction. One of them is kinetic friction. The other one is static friction. So this is, because it's sliding, it is going to be kinetic friction. So we have what we want to do when we're solving an inclined plane is we want to rotate our paper so that the block isn't actually moving along a diagonal, it's actually moving horizontally. So I'm going to rotate my paper like this, and see how now once I rotate it like this, the incline is now flat and it's moving horizontally. Now how much did I have to rotate the paper? I had to rotate it an angle theta. So I'm going to rotate my paper an angle theta, like that. And once I do that, what you notice is that the normal force is now up and down. The friction force is now horizontal. And it's the weight force that is now diagonal. And in fact, because I rotated the paper by an angle theta, that means that the weight force must have also rotated by an angle theta. Okay? So when you have a diagonal force like this, so the weight force is the one that's diagonal, it's not up and down or side to side, you want to break it up into components using trigonometry. So this component is opposite the angle. So that's going to be associated with sine. So this is mg sine of theta. And this side is adjacent to the angle, which means cosine. Mg cosine of theta. Okay? So then I redraw my free body diagram so that the diagonal weight force becomes two forces. So it's going to be a downward mg cosine theta, and then a horizontal mg sine theta. And then we still have the original forces that these two that were already there. All right, so this is what is going to make the problem solvable, is we have all the forces are either up and down or side to side. Now, because the block is not moving perpendicular to the incline, it's not passing through the incline, it's not lifting off the incline, that means that the net force in that direction has to be zero, because if the net force was not zero, it would be moving, accelerating in that direction. So these two have to be equal and opposite. So they basically cancel each other out. And in order to cancel each other out, they need to be the same size. So that means that the normal force is equal to mg cosine of theta. They're opposite in direction, but equal in size. And that then allows us to determine the friction force, because the formula for kinetic friction is mu sub k times normal, where mu sub k is a property of the interface between the two objects that is called the coefficient of friction. So I can then plug this in right here. All right, so I have mu sub k mg cosine of theta, like that. Then, so now this is mu sub k mg cosine of theta. So now, because these two are equal and opposite, they cancel each other out. So we can basically forget about those two. And so what I can see is that the net force, because these two cancel out, it's going to be the positive force minus the negative force. So it's going to be mg sine of theta minus mu sub k mg cosine of theta. So that's the net force. So now I'm going to rotate my paper back to where I was originally. So Newton's second law, which is certainly the most important equation in basic physics, says that net force equals mass times acceleration. The net force, as I said, was this. So that means that mg sine of theta minus mu sub k mg cosine of theta equals ma. Every term has m in it, so the mass cancels out, and we can determine that the acceleration is g times the quantity sine theta minus mu sub k cosine of theta. So there are a couple of things that could change in this equation. So for example, here the block is sliding down the incline, but it is possible for the block to slide up the incline. Maybe you kicked the block so that it's now going up the incline. In that case, because friction is always opposite the direction of motion, in that case, you are going to reverse the direction of friction, and that would change the sign of this term, because this is the term that comes from friction. Another variation is you could have no friction, in which case this term is just gone, because the coefficient of friction is 0. All right? But I would say if you are preparing for the AP Physics 1 exam, I would highly recommend that you are make sure that you can go through all these steps without any reference. So I would study this, and then I would take the notes away and try and reproduce what I just did. All right? That's really important. Just like you would memorize vocabulary in a language class, you want to become really ultra familiar with the inclined plane so that you can do it easily and quickly in a time crunch kind of situation. All right. The next really important forces type problem that I want to talk to you guys about is quasi one-dimensional systems. So these are systems where we have usually a rope is involved and pulleys. So ropes and pulleys. And these are systems where they only can go forward or they can go backward. So here's an example of a quasi one-dimensional system. You've got like a table. That table has a pulley on the end. There's a mass on the table. There's a mass dangling from the table. Those two masses are connected by a rope. Okay? I'm going to give these masses sizes. So there's M2 and there's M1. And we are going to assume in this case that it is a frictionless table. So this is a quasi one-dimensional system. So even though one block is moving horizontally and the other one is moving vertically, really there's only two ways this system can go. M1 drops and M2 moves to the right, or M1 rises and M2 moves to the left. So there's only two directions, forward and backwards. What you want to do with this type of system is you want to define a positive direction, a positive sense of motion. So I think it's fairly obvious that M1 is going to drop, and so I will choose this to be the positive sense. So what that means is the positive direction for M1 is actually downward, and the positive direction for M2 is rightward. So let's start off with free body diagrams for M2 and a free body diagram for M1. M1 is pretty straightforward, okay? It's got its weight force pulling it down, which would be M1G. And then it has the tension from the rope preventing it from falling as fast as it would like to, okay? Tension is the force from a rope. If we look at, and by the way, there is no normal force for M1 because M1 is not resting on a surface. You need to be in contact with the surface in order to have a normal force. And because it's dangling by definition means you're not in contact with something. For M2, M2 is in contact with the surface of the table, right? So it is going to have a normal force. It has its weight force. So that should be M2G. It has no friction, so there is no friction, but it is being pulled to the right by the tension of the rope. Okay? Now, because the M2 is not accelerating up and down, these two forces are equal and opposite. Okay? And so as a result, they just completely cancel each other out. And so we can just kind of ignore those. So for all intents and purposes, M2 has only tension acting on it. Furthermore, one of the things I taught you is that the tension is the same throughout a rope. Okay? So as long as it's the same rope. If you have two different ropes, then you can have two different tensions. But if it's the same rope, it's the same tension. So these two tensions have the same size. Okay? So now let's go ahead and write Newton's second law for M1. And we're going to write Newton's second law for M2. Newton's second law is net force equals ma. M1 has two forces acting on it. Oh, so there's a question in the chat. Sorry, I'm just seeing that. Is it ever possible to truly get a frictionless surface besides space? No, but it is not. Actually, in some situations, you could think of something like a superconductor. A superconductor is an object that has no electrical resistance. And if you start current in a superconductor, electric current, it'll just keep going and going and going forever. And that is a truly frictionless situation. So so I would say, yeah, it is possible, but it's it's using an area of physics called quantum mechanics, which is different from classical physics. So yeah, so I would check out superconductors if you want to read about a frictionless situation. There's also a question in the chat, which is, how do you determine the direction of tension? Tension is always along the rope. So for mass 2, the rope is horizontal, so tension is horizontal. For mass 1, the rope is vertical, so tension is vertical. All right? And you can't push something with a rope. Ropes only pull. So it's always, you know, the tension force always goes in towards the body of the rope, not away from the rope. All right, so for mass 1, downward is the positive direction. So the net force is going to be m1g minus tension. Okay? The reason it's not tension minus m1g is because I have defined positive to be downward. All right? And then the mass of this object is m1. So there you go. For mass 2, rightward is the positive direction, and tension points rightward. So tension is a positive force, and that's the only force because these two canceled out, and that equals m2a. These two accelerations are the same because because these two masses are connected by a taut rope. Okay? If the rope had, so when I say taut, I mean it has no slack. It's completely tight. So then we want to solve for the acceleration, so we add these two equations together. And so when we add these two together, you can see we have minus t and then plus t, so they cancel out. So all that's left on the left-hand side is m1g. On the right-hand side is m1 plus m2a. Divide both sides by m1 plus m2, and I get that the acceleration is m1g over m1 plus m2. Nice. All right. So that's a little review of forces. So I want to talk about experiments to verify Newton's second law. Okay? And Newton's second law is, of course, net force equals ma. So next week when we return to class, we're going to do exactly this. We're going to do an experiment to verify Newton's second law. That's the first thing we're going to do. All right. So here's the experiment that we're going to do to verify Newton's second law. So this is one example of many experiments that you can do to verify Newton's second law. We're going to have an inclined plane. Okay? And that inclined plane has some angle. The angle is not really important, but it's sloped. Okay? Then we are going to have a cart. So this cart is going to want to roll down the incline because it's sloped. But what we're going to do is we're not going to let it roll down the incline. At first, we're not going to let it roll down the incline. We are going to have a spring scale. Okay, so a spring scale is basically you'll see them once we're in class, but it's a little device and it has a hook on the end, and the amount that the hook is stretched is related to the force. So you can just read off the force. Okay, so this is a spring scale, and it measures force. So basically what that's doing is it's telling us how much force is pulling this cart down the incline. Okay, so so we would have a measurement of net force. Okay, because that comes from the spring scale. And then once we've done that, we would let the cart roll down the incline. So we remove the spring scale, we let it roll down the incline, and we time how long it takes to get to the bottom. Okay? So there are ways that we'll talk about in class about how to do that as accurately as possible. So the method that I would use is you would actually record this with a camera. So let's say like this, you know how directors are like, oh, let's see what it looks like through the frame. So there's the frame of the camera, and in the frame of the camera, you would have an iPhone that has a clock running. Okay, so you can see what is the time when it is at the top of the ramp and what is the time when it's at the bottom of the ramp, and then you can subtract those two times, and that's how much time it spent rolling down the ramp. Okay, so you'll have a time and a force. But Newton's second law doesn't have to do with time. T isn't a variable, so we have to convert this to an acceleration. And we would use the fact that that it is accelerating uniformly. So we have this kinematics equation, delta x equals v naught t plus 1/2 at squared. All right, delta x is the distance that it travels down the ramp. The cart starts at rest. All right, so we have delta x equals 1/2 at squared. And then we can solve for the acceleration. The acceleration is 2 delta x over t squared. So for example, what if this distance was 5 meters? And what if it took 2 seconds to go down the ramp? All right, then that would be 2 times 5 over 2 squared. So I would deduce that the acceleration was 2.5 meters per second squared. Okay, so you would use that to convert the data table. So this is called processing your data. Okay, because oftentimes what you measure is not it's related to the quantity that you're really trying to get at, but it's not the quantity that you're. Okay, so you have to manipulate the data to put it into a form that is the form that you want it to be in. Okay, so that you have a data table that is net force versus acceleration. So now how could we change the net force? Well, you could make the ramp steeper. If it's steeper, then there's going to be a bigger force pulling the cart down the incline. So you do a bunch of different steepnesses, and you get a bunch of forces and times, and you convert that to a bunch of forces and accelerations. All right. Then what you would do is you would put net force on the vertical axis and acceleration on the horizontal axis, and you would graph it. Now, what is the prediction of Newton's second law? Well, if we have net force, this is Newton's second law. We have net force on the vertical axis, so net force is like y. We have acceleration on the horizontal axis, so acceleration is like x, and the thing that multiplies x is the slope. So it should look like a straight line, and the slope is the mass of the object. All right? That is the prediction of Newton's second law. All right? Now, it is not necessarily true that that's what you're going to see. You could see something like that looks like this. I don't know. Your data does not necessarily have to show Newton's second law, okay? That means that one of two things has happened. One of the things that could happen is you discovered new physics. It's possible. It's unlikely because Newton's second law has been verified over and over and over again throughout human history. The second possibility is that you did something wrong, okay? So maybe you didn't account for something. Maybe you mismeasured the distance that it traveled, or your time measurements weren't very accurate, or you processed the data incorrectly, okay? So there are all kinds of things that can make your data not match the prediction, okay? And it's a really challenging thing to figure out what that is, to identify what caused the mistake. But it's just part of science, okay? So this experiment, what we did was we applied a force on an object. We applied a certain force by putting the ramp at a certain angle, and then we observed the acceleration. That's one way to do it. Another way is you could apply the same force on different sized objects. Different sized objects, and then observe the acceleration. Okay. So in that case, your data table is going to be acceleration and mass. Okay. So that means that your graph that you make is going to be acceleration and mass. All right. So what does Newton's second law say a graph of acceleration versus mass should look like for a constant force? Well, let's look at it. Net force equals ma. Again, we're applying the same force no matter what. Dividing both sides by m says acceleration equals net force over m. All right. So we have acceleration on the vertical axis. So acceleration is kind of like y. We have mass on the horizontal axis. So mass is acting like x. And notice how m is on the denominator, so that means x is on the denominator. And the net force is constant because it's the same force, so this is just a constant. So you can try and type that into a graphing calculator. If you type in y equals a constant over x, you will see that the graph kind of looks like this. All right, so this is the Newton's second law prediction. And your data hopefully would look something like that. All right. So these are two examples of experiments that we could use to verify Newton's second law. But let's just talk in general. So what is the basic idea when testing a law? Could be Newton's second law, could be some other law, okay? The basic idea is what we want to do is we want to apply the law to some scenario. And I'm going to say some accessible scenario. You know, because we're going to do an experiment, right? So if we can't do the experiment, that's not an accessible scenario, so it's kind of pointless. All right. So we apply the law to some accessible scenario, some scenario that we can actually realize in the physical world. And then what we do is we calculate what should happen based on the law, assuming that the law is true, okay? Then we do an experiment. So this is why the scenario has to be accessible, right? Because we have to be able to do the experiment. If we can't do the experiment, then we're not doing science, okay? We're doing philosophy instead. So you do an experiment and you measure what actually happens. Okay? So when you're figuring out what should happen, you calculate. But when you're seeing what actually happens, you measure. Okay? And then you compare those two. If they match, then that is evidence in support of the law. So you can start to gain confidence in the law, all right? And for example, in Newton's second law, many people have done experiments that have all confirmed Newton's second law. So we have a lot of confidence in that law. So there's not a lot of people who are experimenting with Newton's second law because it has been verified so many times that we have a great amount of confidence that it is true, okay? If they don't match, then that's a little bit more tricky, okay? One possibility is that you found new physics. So this is actually happening right now. You might have heard in the news that that there has been some evidence for a possible fifth force of nature. So there are four fundamental forces in nature: gravity, strong force, weak force, and electromagnetic force. But we calculated what should happen, and then we did an experiment, and they did not match. They did not match. So some people think that we have found new physics, all right? But there's another possibility, or we messed up. So usually if you are messing up in an experiment, you are not accounting for all the factors that could impact the results of an experiment. And these experiments that are measuring these fundamental forces are incredibly complicated. So it is really difficult to tell if you messed up or not. And so this is a really tough thing to do, to differentiate between whether you actually found new physics or if you just messed up your experiment. And so, really what they're going to do is you're going to have a bunch of independent parties repeat the experiment and see what they come up with. Okay? So when experiment and theory do not match, people get excited because that means everyone's going to start doing the same experiment or variations of it and seeing what kind of results they get, and then we can kind of reach a consensus on whether we've actually found new physics or if we all messed up. Okay? So that's how science works. And we've just applied that method to Newton's second law. So that's my lesson for today.